In this lesson, we're going to take a look at oxidation numbers. So oxidation numbers are an arbitrary assigning of a charge. So we're talking about redox reactions, so reduction and oxidation half reactions, and how there's a gain and loss of electrons happening in those reactions. So if we think about ionic compounds are created by a bond between a positively charged ion and a negatively charged ion. And those become positively and negatively charged because of a gain or loss of electrons. So sodium has lost a negatively charged electron, making it charged with a 1+ charge, and chlorine has gained that electron, so it makes it a 1- charge. So here we have an actual gain or loss of electrons happening, which gives charges to each of these. So we have actual ions created here. In oxidation reduction reactions, we don't always have ions created, but we still have electrons that may be closer to one of the atoms or another, and so we assign it a positive or negative charge. So if we think about the molecule water, the bonds in that are covalent, which means that the electrons are shared. But they're not actually shared equally like shown in this diagram. So if you recall, we have talked about how water is a polar molecule and it has a slightly negative and slightly positive end. And that is because the electrons that are shared between the hydrogen and the oxygen are actually pulled in a little bit closer to the oxygen than to the hydrogen. So the one electron that hydrogen has shifted closer to the oxygen, which makes it seem as though hydrogen has a +1 charge because it's like it's lost an electron. Now it's not fully in oxygen's valence shells, but it is closer to oxygen than to hydrogen. And the same thing happens here with this hydrogen. The oxygen, on the other hand, has 2 electrons that have come closer to it, so one from each of the hydrogens. So that we would say then has an arbitrary assigning of a 2-, and then the H's are each a+. So we don't have a full gaining or losing here, so we don't have actual ions created, but because the electrons are pulled closer to one of the atoms, we are assigning arbitrarily negative and positive charges based on whether electrons are closer to an atom or further away from an atom. And so we saw when we talked about polar molecules that does create a negative and positive sort of area of a molecule. Okay, so the rules that we have for assigning oxidation numbers: anything that is on its own, so a potassium atom, the element oxygen, a nitrogen atom, a lithium atom, anything that's completely on its own is going to have an oxidation number of 0. So that is providing it is neutral as these are. If something is an ion, so it has actually gained or lost electrons, then the oxidation number is going to be the same as that charge. So if I have a magnesium ion that has lost 2 electrons, so the oxidation number is a +2 here. For hydrogen is generally +1, but there are exceptions when it is combined with a metal to make a metal hydride. So for example, sodium hydride. Over here, the sodium gets the +1, which comes from this rule, and the hydrogen is a -1. Or we could figure out that the sodium is a +1, because our exception here tells us that hydrogen is a -1 when it is with a metal. The oxidation number for oxygen in almost all compounds is -2. So over here we have H2O, so the 2 hydrogens are each a 1+, so I have a 1+ and a 1+, and then a 2- from the 1 oxygen, so that gives me the neutral overall in the water. MgO, so this we can use our ionic because there is an actual gain or loss, so I have a metal and a non-metal, So magnesium is a 2 plus, it loses 2 electrons, and oxygen is a 2 minus. So one of the exceptions to that is the oxygen in hydrogen peroxide is 2 minus. So here the hydrogen rule stays where each hydrogen is a +1. So I have +1 and +1 for the 2 hydrogens. And so to balance out, to give me a neutral overall, which is what H2O2 is, each oxygen would be a -1 to balance that out. Everything in group 1 is a +1, and everything in group 2 is a +2. Any compound, so something that is neutrally charged, the sum of its oxidation numbers has to equal 0. So we have rules for certain elements here, or groups in periodic tables, and other things we can figure out based on this rule where the sum has to equal 0 for a compound, or if I have a polyatomic ion, then the oxidation numbers of the polyatomic ion have to equal whatever the charge is. So for example, hydroxide is OH with a -1 charge. So oxygen has a -2, hydrogen is a +1, and when I add those charges, I get a -1, which is what the overall charge of OH minus is. Okay, let's take a look at what this looks like. So I have strontium bromide here. Strontium is a metal, bromine is a nonmetal, so this is an ionic, which means there's an actual gain or loss of electrons. So here strontium is in group 2, so it's going to be a 2 plus. Now we could also have looked at the rule for everything in group 2 is a 2 plus. So Br2 altogether has to equal 2 minus to balance out to give the 0 charge overall, which means each bromine is going to have a 1 plus. So when we write, a 1 minus, not a 1 plus. So when we write our numbers, 1 minus. So when we write our oxidation numbers, it is for just one atom of each element. If you want to above keep track of the total so that you can see that it's neutral, so bromine, I have 2 atoms of bromine here, which means that overall there's going to be a 2 minus, and then the 2 plus and 2 minus will cancel out. So another thing that I haven't mentioned yet, so with ionic compounds, one of the reasons we have a full gain and loss of electrons is the difference in electronegativity. That is the thing that in covalent compounds as well will pull electrons closer to one of the atoms, but perhaps not fully pulling that over in a covalent compound. So we have this slightly positive, slightly negative area, but there hasn't been a full gain or loss of electrons. Okay. HClO4. So here we have a rule for hydrogen, which is hydrogen is a +1. Now chlorine has multiple oxidation numbers that it can have. Oxygen is a 2 minus or -2. So overall I have 1 hydrogen, so I have 1 plus. I have 4 oxygens, each at -2, which is a -8. And overall this has to equal 0. So I have +1 plus whatever chlorine is -8, and that has to equal 0. So that must be a +7 then. So +1, a +7 is +8, and then I have -8 from the oxygen. So overall, I have 0 overall for the compound, which was one of the rules as well. This isn't charged. And then the other thing I could look at is polyatomic ions have to equal the charge of the ion. Chlorate has a charge of minus, and so if I take a look, the +7 and -2, so this was +7 and -8, so 7 subtract 8 is -1, so that worked for that rule as well. So there's often multiple ways that you can calculate the oxidation numbers. Okay, we'll do one more here. So here I have a polyatomic ion, and so overall it needs to equal 2 minus. I have 7 oxygen, so this is one that you'll probably get to know well, that oxygen is a minus 2. So oxygen is minus 2, that means 7 times 2 is a minus 14 overall, and whatever chromium is, I have 2 of it, and then oxygen is a negative 14, and overall that has to equal negative 2 because the charge is negative 2 overall. So the 2 chromiums together need to equal negative 2 plus 14, or 12, which means each chromium is equal to a positive 6. So for each chromium, I would write plus 6 on the bottom, and if I want to keep track, that's a plus 12. So 12 take away 14 is equal to the negative 2 there. So one of the reasons that we do this, we can use this to balance equations, but the other thing we can do is use oxidation numbers to figure out if we have a redox reaction happening or not. So here I have zinc and sulfur, each completely on their own. So when something is completely on its own, if it doesn't have a charge, it is a 0. And then I have zinc sulfide, which is an ionic compound. So there's an actual gain and loss of electrons happening there. So zinc would have lost 2 electrons to sulfur, which would have gained 2 electrons. So because it's ionic, actual gain and loss, I can figure this out with the fact that sulfur is in group 6, which means it needs to gain 2 electrons to be happy, to have a full outer shell. And so that's going to give it a minus 2 charge, which means zinc has to have a plus 2. So within each element, I can see that I have had a shifting of electrons. And once again, in this case, there's an actual gain and loss. So zinc has lost 2 electrons, sulfur has gained 2 electrons. So here there is a redox reaction happening. So I could write my half reactions. Zinc is going to split into the ion and 2 electrons. So remember, each side has to add up for charges. So I have a 0 here, 2 plus, 2 minus, which gives me a 0 total on this side. So here there is a loss of electrons. So if you remember from Leo Ger, a loss of electrons is oxidation. So this is my oxidation reaction. So zinc is getting oxidized. It makes it the reducing agent because in losing electrons, it's allowing for something else to get reduced. Sulfur, on the other hand, is going to gain 2 electrons and become a negatively charged ion. So over here I have a 0 plus 2 minus, so overall 2 minus, and 2 minus on this side, so that is also balanced for charges. So this gained electrons, Leo Ger, gain of electrons, is reduction. So sulfur is reduced, and it is also the oxidizing agent because by gaining electrons, it allows something else, zinc in this case, to be oxidized. Okay, one more example. So we'll take a look at each of the numbers here. So SO3 is overall neutral. Oxygen is 2 minus. I have 3 of them, so that's minus 6 total, which means sulfur needs to be plus 6 to end up getting to 0 there. Water, hydrogen is plus 1. I have 2 of them, which makes it plus 2, and I can either look to the fact that it's neutral, or oxygen also has a rule that it's minus 2, plus 2 and minus 2 equals 0, and that is neutral. And then sulfuric acid, which is also overall neutral. So a couple ways I can look at this. Hydrogen is a plus 1. I have 2 of them. And then sulfate is a polyatomic ion. So here sulfuric acid is also ionic. So we have a full gaining and losing of electrons. So hydrogens become plus 2. Sulfate is 2 minus overall. So oxygens have a minus 2. There are 4 of them, so minus 8 overall. and either the sulfate needs to add to -6 or the entire thing needs to add to 0. So it doesn't matter what we do. So if we do the entire thing, we have +2 for hydrogen. Our sulfur, we don't know, there's only one of it. And oxygen is a -8, and that needs to equal 0. So that's equal to 6. So the other thing we could have done is just use the polyatomic. So sulfur, sulfate, the 1 sulfur minus the 4 oxygen needs to equal -2 because sulfate has a 2- charge. So then I have x equals -2 plus 8, which is equal to 6. So either way works there. So I have a +6, so everything there adds up. Okay, sulfur goes from +6, and it's still +6. Oxygen is -2 here, -2 here, and -2 here. Hydrogen is +1 and +1. So in every single compound here, each element has kept the same oxidation number, which means however it is combined with other atoms, how close the electrons are to each atom hasn't changed. So it hasn't shifted to electrons being closer to an atom in the products than in the reactants or the reverse. So here there is no redox reaction going on. So there's no gain and loss of electrons happening. Okay, practice questions. So the first set here are to practice oxidation numbers, and then the second set here are practicing oxidation numbers to decide if something is a redox reaction or not. And these are in the old textbook.